This video, we're going to take a little bit of time to introduce what's called the dot product. So the dot product is a way that we can multiply vectors together using what you see defined on this screen that has some geometry associated with it that's very beneficial for us to be able to utilize. We're not necessarily going to get into the geometric implications of a dot product calculation. This is just going to kind of be to introduce the notation, the terminology, and to do a quick example. So dot product between two vectors, it can be for three-dimensional vectors like you see defined across this top line. It can be for two-dimensional vectors like you see across the bottom line. But a dot product is defined with the dot symbol for multiplication. It's a calculation that you do between two vectors, and it is a super easy calculation to do. All you do is you multiply the x components of the vectors together, add on to that the y components multiplied together, and then add on to that the z components multiplied together. For a two-dimensional dot product, you do the same thing, you just don't have the z components to worry about. What you will notice about this calculation is that if I'm multiplying the x components together, this is just a number, this is just a number, and this is just a number. So if I'm adding together three values that are just numbers, I don't end up with a vector when I carry out a dot product calculation. I end up with a scalar. So you might have a professor or a teacher that refers to this as the scalar product as opposed to the dot product, but the symbol that represents it is the dot for multiplication, and then the calculation you do, we just talked about within this definition box right here. What we will eventually talk about is we'll talk about what's called the cross product. So the cross product for vector multiplication is going to be defined with the cross symbol for multiplication, which is for some reason difficult for me to try to draw right now. But the cross product is a way that you multiply vectors together that gives you a new vector. In term, you'll have to kind of be paying close attention. Do you see the dot as what's between your vectors? If that's the case, you're looking for a scalar answer. Do you see the cross symbol for multiplication between your vectors? If that's what you see, you're looking for a new vector for the answer for that situation. So the dot product should be pretty easy to handle. There's some properties here that we'll kind of briefly just talk about. We aren't necessarily going to prove any of these within this little introductory video. But the dot product is commutative. Doesn't matter which order you do it in, and that shouldn't surprise you. You saw the operations there were multiplication and addition. If those operations are commutative, it should make sense to argue that the overall dot product calculation is also going to be commutative. We have a distributive property defined for dot products. So if I have two vectors added together, and I'm taking the sum of these two vectors, and I'm doing a dot product between that sum and another vector, what I can do is I can actually distribute the vector A into both of the vectors B and C with addition as the operation between. You can factor constants out in front. So scalars, essentially, it doesn't matter where you do the scalar. It can multiply A, it can multiply B. You can do the dot product first and then multiply by the scalar at the end. When you do a dot product with any vector and the zero vector, your answer is 0. And if you do a dot product between a vector and itself, what you're going to end up with as your answer is going to be the magnitude of the original vector squared. So a couple quick examples here. We just want to compute dot product between A and B. So for the two-dimensional version, we're just going to multiply the x components together, multiply the y components together, boom, we've got our result. This one is a little bit different. Obviously, it's a different notation with the way the vectors are presented. What you will notice is you'll notice an I, you'll notice a J, and you'll notice a K. So although each of these individual vectors only have two components, they really are three-dimensional vectors because of the inclusion of unit vector K. So keep in mind that unit vector I, the coefficient of that represents the x component of that vector. So if I'm multiplying the x component of vector A together with the x component of vector B, I'm going to take 2, and then since there's no I over here, I'm going to assume that the x component of vector B is 0. I'm going to take the y component of vector A, and there's no j in vector A, so the x component of vector A must be 0, and then times, I think I said x component, I'm sorry, I meant to say y component. There's no y component for vector A, so coefficient for the y component is 0, and then the y component of vector b has a coefficient of 4. So multiply the y components together. The z components are going to be given by the coefficients of those unit vector k's. That's going to be -1 for both vectors, so if I multiply those together and then add the results, you end up with 1. So in the next video, we'll talk about some of the geometry associated with this calculation that we've introduced here.